Okay, so good morning, everyone. So today we cover the part about cosmic ray, so indirect detection of dark matter with cosmic rays, and in particular we start with positrons. So the propagation of positrons, as I told you a few lectures ago, takes into account mostly time dependence in the density distribution. Then you have the diffusion coefficient. Then you have convection that depends on the velocity of convection. Then you have energy losses that in principle are changing with space. And then you have the reacceleration. And finally, a source term. So the source term, in case of dark matter, and in particular of annihilation of dark matter, takes into account the density squared, the sigma v, and the source spectrum of dark matter. This is what we saw yesterday at the beginning of the lecture of yesterday. So this is the average number of E plus E minus produced per dark matter annihilation. For the diffusion coefficient, we can take something that is basically a power law in rigidity. This is what plasma physics tells us about magneto-hydrodynamic waves propagating in a plasma. Or you can use a more complicated shape, for example, a double broken power law. Well, it's not important to see the parametrization, but it's basically a broken power law, double broken power law. And in particular, the shape of diffusion coefficient with rigidity, in this case, as you can see, is here there is a hard spectrum, a change of slope at about a few gigavolt, and another change of slope here at about a few hundred gigavolt. So this is required in order to fit the change of slope of cosmic rays at low energy. Here you have a lot of uncertainties due to the solar modulation, but regardless this uncertainty, you still need this quite big change of slope. And instead, this other change of slope is needed to fit the change of cosmic ray flux for all the primaries. And what is very interesting is that this change of slope is quite smooth, okay? So it's not a broken power law, but it's a smoothed broken power law. And the smoothing is quite pronounced. Okay, so you can fit your propagation to proton, so basically primary and secondary cosmic rays. And another important factor is the energy losses. We saw in the last lectures that we have synchrotron radiation, inverse Compton scattering, Coulomb ionization, and Bremsstrahlung. Typically, when you include all these energy losses, you have a shape of the energy losses with energy that is roughly B0 e to the 2. Okay, so it is going with the square of energy. Then if you do the calculation properly, actually it's not exactly to the 2 across all the energies. But if this is 1 GeV, 10 GeV, here is 1 TeV. Typically for a Bremsstrahlung, Coulomb ionization, you have a slope like this, so e to the 1.5. Then it converges to something like e to the 1.9, and that for high energy, when you have synchrotron, it goes to, this is actually e to the minus 2, okay, e to the minus 2 energy losses. So this is where you have synchrotron. Synchrotron radiation scales exactly with e to the 2. This is e to the 1.9, that is basically inverse Compton, and then this is e to the basically 1.5 for Coulomb, ionization, and Bremsstrahlung. So when you take all this into account, you can find that, and when you fit cosmic ray fluxes, you can find a setup of propagation that fits reasonably well the different data. And for dark matter, you still have an issue with the value of the diffusive halo. So you probably remember that we parameterize, basically we model the galaxy has a thin disk of size 100 parsec, but the galactic magnetic field is present also beyond this 100 parsec of the disk. So the size of the galaxy where cosmic ray make a diffusion can reach even 10 kiloparsec for some models. The size of this diffusive halo is not known yet. There is quite a large uncertainty. Taking radioactive materials, radioactive elements like beryllium-10, we know that this diffusive halo should be larger than at least 1-2 kiloparsec. But the upper limit, we don't still have a precise upper limit. So typically this value can range from, let's say, 2 to 10 kiloparsec. For cosmic rays, this is an issue. For basically the astrophysical production of cosmic ray, this is of course an issue. But for dark matter is even more an issue, because dark matter is basically particles generated from dark matter. They are generated from a huge halo with a size of 100 kiloparsec. Okay, so dark matter can produce positrons basically almost in a sphere of 100 kiloparsec. Then of course the density is peaked probably towards the center. No, the density of dark matter for Caspi profile is peaked toward the center. For instead for core profiles is something like this. But in principle, you can have production of positrons even in the outer part of the Milky Way halo. Instead of astrophysical production, the production is focused on the galactic disk. Okay, so the astrophysical E+, E-, and cosmic ray, they start from here. So the probability for them to escape is less with respect to the ones generated from dark matter, because dark matter can produce a positron even here. Okay, and so typically for dark matter, it's even more important the estimation of the diffusive halo size. So physicists in the past, like David Morin, Fiorenzo Donato, Pierre Salati, made a model, min-med-max, where they fitted cosmic ray data, and they found what could be the variation of the flux of positrons and antiprotons from dark matter, and they were finding that with that time knowledge of propagation, the flux could vary even a factor of 10. Okay. Nowadays we have better data, more precise, and Genolini, David Morin, and collaborators made a new estimation of this min-med-max model. We have now an estimation of the diffusive halo size that is more precise than what they had in the past. And nowadays, the variation of the positron flux from dark matter, for example, from the BB bar channel or the plus and minus channel, is a factor, let's say, of 30–40%. So now the possible variation of dark matter flux of positrons is much less than what it was in the past. Okay, so basically thanks to the new estimation of the propagation, we have more precise estimation also of the possible flux from dark matter. But as I told you in the last lectures, in order to have a high discovery potential for dark matter, you need to know very, very well the astrophysical emission of your particle. So in this case, for positrons, what is the possible, or let's say, what is the known astrophysical production of positrons? We have at least two. One is, you remember? Yeah, for positrons. What are the known astrophysical mechanism that generates positrons? The scattering, exactly. So the secondary production, so scattering of cosmic rays, primary cosmic rays against atoms of the interstellar medium, this could generate positrons, also electrons, and whatever else. Or you also have pulsars, okay, pulsars that are rapidly spinning neutron stars. They have magnetic fields so extreme that they extract couples of particles and antiparticles that for showering they create also positrons and electrons. Okay, so let's focus on secondary production. So for secondary production, we have to evaluate a source term that is the sum on Ij. Ij are the cosmic ray interstellar medium atoms species. 4 pi density of interstellar medium atoms, and the integral in the kinetic energy of the cosmic ray, flux of the cosmic ray, and then you have the differential cross-section for the collision between the cosmic ray and the atom of the interstellar medium. Okay, so this is very reasonable because this process should take into account a convolution of the flux of cosmic ray interacting against atoms of the interstellar medium. This integral should be convolved on the cross-section, and the 4 pi is because you have an isotropic production. So so for the interstellar medium, we have more or less a good knowledge. So the interstellar medium is focused on the galactic disk. Most of that is hydrogen. Then you have helium and heavier elements. And we know more or less the spatial distribution. The flux of primary cosmic rays, also we know this from AMS measurement. So the key point is to extract and measure the cross-section. So for who has just come, I'm explaining the secondary production of positrons. Okay, so the production of positrons from collision of cosmic rays with atoms of the interstellar medium. How do we evaluate this cross-section? This cross-section is evaluated by fitting analytic functions of the cross-section to the data. We have a very rich data set of data for the production of pions. So basically the production of positrons and electrons follows not exactly this table, but is, let's say, most of the production comes from proton-proton against pi plus. Sorry for this is the table for gamma rays, but it's similar for electrons and positrons. So proton-proton pi plus, or that gives kaons, or lambda particles and eta. Very, very luckily, we have a very rich data set for the production of pions, kaons, and lambda particles. Here you see the coverage of this data for center of mass energy from, let's say, a few GeV up to basically the LHC energies. And so what we did with Fiorenzo Donato, Luca Usa, and collaborators, we fitted the invariant cross-section that is energy d3 sigma over the P3. Okay, so this is a Lorentz invariant way for writing a cross-section. And most of those data are exactly for this invariant cross-section. Then we parameterize this as a cross-section as a function of square root of s. This is in particular the inelastic proton-proton cross-section plus a function of square root of s, pt, and xr or xf that we fit to the data. Okay? Okay, then in order to go from the sigma invariant and this one, we just integrate over some kinematic variables in order to just have the energies of the proton and the one of the positron. Then when we do this, yes, then another important thing. So these cross-sections are for the productions of pions, kaons, K0s, K0l, and lambda. But we need the cross-section for the production of positrons. So how can we go from the cross-section for the production of mesons and baryons to the one of the production of positrons? Can you imagine how we can do that? Sorry? Exactly, we just take into account electroweak decays. That is a very well-known physics. So we take basically the cross-section for the decays and you convolve, basically you integrate the cross-section for the production of positrons. It's basically the integral on the energy of, for example, the pion, or for the distribution of the energy of the pion evaluated for the electroweak decay of the pion producing positron electrons, okay? So we need this additional step that is not needed in the case of anti-proton cross-section, okay? So in the case of anti-proton cross-section, so proton-proton producing anti-proton and X, for example, if you have proton-proton producing lambda, then the lambda decays into an anti-proton, do you think we need this step for going from the production of lambda to the one of anti-proton? The answer is no. But the reason is, why? We very likely don't need this step of convolution. The reason is that if you start from a pion, the pion has a mass of 130 MeV, then it has to create a positron that has a mass of 500 keV. keV, yes, 0.5 MeV, plus something, okay? So the distribution of the positron is very broad, can take a lot of different energies. Instead, the lambda particle has a mass of the order of the antiproton. It's just 1.4 GeV, if I remember correctly. And the other particles produced are very, the mass is much, much smaller, okay? So in the decay of the lambda into the antiproton, all the kinematics of the lambda basically goes into the antiproton, okay? So the distribution of the energy from the lambda, the distribution of the energy on the antiproton is basically picked in a very narrow shape into the energy of the lambda, okay? So typically when we do the cross-section for the production of antiproton, we don't take this step into account. Don't antiprotons have higher energy? No, yes, but we don't care about, so in this distribution, we just want to check whether, given a lambda with some energy, what's the possible energy of the antiproton? This was just what I'm talking about, okay? Then, of course, this antiproton can produce lambda with several different energies, okay? But the point is, given a lambda with a given energy, what's the distribution of energies for the antiproton? The answer is that is basically centered on the lambda particle energy, okay? Okay, so if we take into account the cross-section fitted to the data, we take the source term, we propagate the source term, well, first we get an uncertainty on the positron cross-section that is less than 1%. Okay, the result is in this band. This band is the uncertainty for the production cross-section that is less than 10%. And this is a remarkable result. And then for the secondary production, we get a secondary production with respect to AMS positron data, for which it's clear that something else is needed, right? Because the data points are not on top of the bands. These 3 bands are for 3 different propagation models. They include either only convection or only reacceleration, or different assumptions for reacceleration and convection. But regardless the model that you pick, it's clear that something else is needed. This instead is the prediction for a model with convection with different diffusive halo size. And you can see that basically all the halo sizes are compatible with the data. None of them is ruled out, but still something is missing, okay? So what is the next object that can generate positrons is a pulsar. In the galaxy, we have detected basically 3,000 of pulsars from radio to gamma rays, okay? These are the most local and powerful pulsars. And there are studies like from myself and colleague, Cholis, Denuper, Serpico, where basically we all found that pulsars can contribute to the high energy of the positron excess. So in this paper in particular, we have taken a synthetic population of pulsars. So we simulated the population of pulsars taking the spiral arm distribution of sources in the Milky Way. We simulated sources with the distribution of luminosity function, with the distribution on speed down luminosity and periods. So using very reasonable distributions for the characteristic of the pulsars. Then we inject from the pulsars the positrons, and we propagate these positrons in the galaxy. One of the key parameters is the efficiency for conversion of pulsar energy into positrons. And this is a very important parameter because the efficiency is telling us how efficiently pulsars convert energy into positrons. You might remember from HAWK, we see gamma rays around Geminge monogem. Do you remember that for very high energy gamma rays? So in gamma rays, the HAWK experiment has measured an extended emission around Geminge monogem. You remember that we saw this? No, okay. Just to recap this part. So the HAWK experiment that measures very high energy gamma rays, they have detected a very extended emission of gamma rays around Geminge monogem. And these very high energy gamma rays are very likely inverse quantum scattering of E plus E minus generated by the pulsars and making the scattering against low energy photons. Okay, so the discovery of these photons is an indirect way of studying the injection of positrons by pulsars. Okay, in order to fit those data, you need an efficiency of the order of 10%, more or less. And in fact, by using an efficiency between a few percent up to 10%, we can fit with the synthetic population of pulsars the data. Okay, so all goes in the same direction. Gamma ray observation of pulsars is telling us that pulsars accelerate positrons. And we can use more or less the same efficiency to fit a positron excess. Okay? Ah, yes, yes, right. Thanks for asking. Yes, I forgot to mention this. So when you do these simulations of pulsars, you can have basically two benchmark cases. One is that where you have basically a single pulsar that is much brighter than the others. This pulsar has a shape that follows the data. Okay, actually the data are basically flat and they started to have a decreasing shape. Okay, if the age and the distance of the source is it takes some specific values, you follow pretty well the data. In this case, the total contribution is smooth, let's say by construction, no? Because it's one single pulsar and the emission of the single pulsar is smooth. Instead, if you have more sources that are contributing, you still need one dominant pulsar at low energy, but you could have other pulsars with a smaller contribution. And if the pulsars are young, so let's say below 100 kiloyears, they inject spikes at high energy. Why do you need that the pulsar is young and close for very high energy positrons? So could a old and distant pulsar contribute to positrons beyond 1 TeV? Possibly. It's very difficult, because keep in mind that very high energy positrons lose energy very, very efficiently. So if you have a pulsar at 2 kiloparsec, it's very unlikely that this pulsar propagates and reach the Earth with an energy beyond 1 TeV. Okay? So in this case, you have local pulsar young that generates positron up to these energies. And since it is young, you have these spikes. Okay? So in the future, AMS or other future experiments can test whether you have a very young and close by pulsar by looking for spikes in the spectrum. Currently, in the data, you don't have any spike, so you cannot have very, very close and young pulsar. Okay. Also, keep in mind that statistically speaking, it's very difficult to have a close by and a young pulsar, because the distribution of ages of pulsar is flat. You have basically an average production of supernova and pulsar in the galaxy. So the probability that you have one pulsar that is very, very young and magically it's inside a small circle around the solar system is not that much. Okay. Yes. Inaccuracy. You were talking about just the last point. Okay. Because the AMS collaboration decided to release the data also for this last point, because it seems, just looking to the average value, that the shape starts to have a cutoff. Okay, so they want to release these results that the data starts to make a cutoff. Okay, the presence of a cutoff in the positron data is very, very important, because it can be, let's say, the evidence of a pulsar with a specific distance and age for which you start to have a cutoff, or it could be the evidence of a dark matter signal, because you remember that the dark matter spectrum has a cutoff when the energy of the particle is above the dark matter mass. Okay, so if you have a cutoff at 1 TeV, this implies that dark matter could be with the mass of 1 TeV. But as I will show you in a few slides, the dark matter interpretation as a dominant contribution is basically ruled out by gamma ray data. Okay, it's a political decision basically to release also that point. Okay, now let's start with some constraints for the dark matter interpretation. So you can try to fit your data just with secondary production plus a dark matter contribution, so without considering pulsars. And the region that fits well the data is this region here, so for a mass of the order of 1 TeV. This is taking the old Pamela data for positrons and the old Egret data for gamma rays. Okay, so this analysis dates back 15 years probably. And as you can see, this region of fitting the positron data starts to be in tension with the upper limits from gamma rays. In particular, these upper limits comes from the analysis of the Milky Way. So you take the unresolved gamma ray emission in the galaxy, and if dark matter injects positrons, you have prompt production of gamma rays plus inverse Compton scattering. Okay, so these authors took the production of prompt inverse Compton from dark matter, and they checked that they don't overshoot the Egret data for gamma rays. Okay, they do this from different observation region of interest. And you see that the yellow part starts to be in tension with the data, with the upper limits. Okay, so the dark matter interpretation is in tension with gamma ray limits, and it has been basically ruled out by using Fermi-Lat data. So Fermi-Lat is the experiment that came after Egret, more sensitive. And by considering a region 3 by 3 around the galactic center, you see that these upper limits are basically a factor of 10 below the region that fits the positron excess. And this was just with, if I remember correctly, 10 months of Fermi-Lat data. Now Fermi-Lat has been taking data since 17 years, meaning that these limits probably are a factor of square root of 17. Okay, so basically a factor of at least 4 lower. Okay, so since you cannot fit data with a dominant contribution of dark matter, you can still try to do some more reasonable study of dark matter, where you try to find some narrow spectral features in the data. In particular, if you have dark matter going into E plus E minus, this channel generates directly E plus E minus. So you don't have hadronization, electroweak showering in between that makes a broad distribution of energy in positrons. Okay, so dark matter, E plus and E minus will have basically the energy of the dark matter mass. And in fact, the distribution of the source spectrum is peaked at, in this case, the dark matter mass is 100 GeV, the distribution is basically peaked at 100 GeV. Okay, this is a delta. You have a low energy tail because you also have other processes like final state radiation. So you can have dark matter, E plus, E minus, but this E plus, E minus can radiate a photon. The photon can make QQ bar, and the QQ bar for hadronization can produce pions that decays into positrons. okay? So in addition to the delta here, you also have a low energy tail. For mu channel, the shape is less peaked at the dark matter mass, the distribution is slightly broader. For tau plus tau minus is even broader. And for BB bar, you have basically a continuum, okay? Now, the idea is that if you want to fit the data with a BB bar, you need to know very well what's the pulsar contribution, because the distribution here is so broad that can fit entirely the positron excess. So if you don't know the pulsar contribution, you don't have a discovery potential to fit this orange curve. Instead, if you want to fit this delta for sure cannot fit entirely the positron excess, okay? So if you have secondary production dark matter, you don't find a good fit to the data. And so you can assume that you have a perfect fit to your data, so something like the black curve, and on top of that, you add the delta of the dark matter contribution. So basically, it's a sort of line search in the positron data. And this brings the results that are shown here, that are the limits for the plus and minus channel. These are robust because, of course, delta is not affected by uncertainty on the pulsar. Mu plus, mu minus also is sort of robust. With tau plus, tau minus, the distribution is too broad, in my opinion, to make limits that are robust, because it's sufficient that maybe you have a pulsar that contributes just in this energy, and if you don't take into account correctly the pulsar contribution with this shape, you have wrong limits for dark matter in tau channel. But for E plus E minus, mu plus mu minus, you see how strong the limits are. So basically you're ruling out the thermal cross-section up to 100, 300 GeV. Okay? So leptonic channels for dark matter are constrained very tightly by the positron data, by AMS. Questions? Okay. So now we can move to antiprotons. So in case of antiprotons, the propagation is, you have to take into account slightly different effects, because the energy losses for antiprotons are not so important. Diffusion is for sure the most important process. And what do you think is the next most important process for antiproton traveling in the galaxy? What can protons do in the galaxy? So protons can collide, antiprotons can collide with interstellar medium atoms. So you have to take into account nuclear cross sections. So exactly as proton against a proton makes particles, so positron, gamma, antiprotons, the same can happen for proton, antiproton. Actually, you have two processes. You have annihilating processes, because you have particle, antiparticle, and so you have to take into account the annihilation rate. And then you have non-annihilating processes. Okay? And these are more similar to this process, proton-proton producing other particles. The rest is quite similar. So here you just have to include also the nuclear cross-sections. And you can safely neglect the energy losses. Okay. Okay, so in this case, so let's recap. What's the main astrophysical production of antiprotons? Is the same as for positrons, right? So the main production is expected to be the secondary one. So exactly as for positrons, we have to estimate the invariant cross-section, okay? For invariant cross-section of antiprotons, we also have a very rich data set. This is actually one of the first papers I did in my career, and at that time we had this data available. But actually later we did updates of these cross sections, and we also have LHC-B data for proton scattering on helium and producing antiprotons. But basically we can parameterize the cross section by fitting all this data, and we find basically a prediction for the secondary source term that has an uncertainty of the order of 15–20%. Okay. This is taking into account the prompt production of antiproton. So proton-proton producing antiproton X. But for antiprotons, you have also other very important mechanisms. One in particular is quite challenging to measure. And this takes into account the proton-proton producing antineutron. Okay? Antineutron decay is not important for collider experiments because the decay time is so long that basically you don't detect the decay on the antineutron in your detector. But for the galactic timescales, the neutron is unstable and you never detect directly this antineutron. Okay? So the antineutron for beta decay makes the antiproton, and then you have the electron. Actually, in this case, you have the positron and the neutrino electron. The problem is that experimentally measuring this production is very, very challenging because the neutron or antineutron is a neutral particle, and it's not that easy to detect neutral particles with colliders. And in particular, Na14, but let's say, what do you expect about this production? So do you expect that proton-proton antineutron, should it be equal to this production? Should be smaller, larger? What's your expectation? More or less the same? Smaller? Why smaller? Exactly. So basically, if you take proton-proton, this is a charge equal to +2, okay? Here you have to make a -1. Instead, here you have to make a 0, okay? So it's probably easier to detect to produce an antineutron with respect to an antiproton, okay? And in fact, this is probably the correct answer because we still don't know. But we expect that basically you should have. So what we know is that the multiplicity of protons and the multiplicity of antiprotons goes in this way. So at low energy, so at high energy, the two are basically the same. Then the one of proton decreases in this way. Instead, the one of antiprotons decreases more quickly, okay? So at high energy, we expect that the one of antineutron should be the same. And where should it stay? In between, right? Because the charge of the neutron is in between the charge of the proton and the one of antiproton. Okay. So this is what we would expect. And we have actually an analogy of this with pions. For pions, we have more measurements, and the multiplicity of production of pi plus, pi minus, and pi zero basically is similar. So you have basically the same number for high energy. For low energy, you have pi minus, pi zero, pi plus. Okay. Experimentally, this is measured quite precisely. Instead, about this, we know the multiplicity of proton-antiproton. Instead, we have no clues about antineutron. No clues except for a proceeding of an A49 experiment where they measured the proton deuterium producing antiprotons with respect to proton deuterium with respect to proton producing no, basically still a proton deuterium making antiproton, but in the deuterium you have the proton and the neutron. So basically in one type of collision they make proton-proton, so the neutron is a spectator. And then they did proton-neutron, where the proton is a spectator. And proton on neutron that makes antiproton X is equivalent of proton-proton making antineutron X. Okay? So with this trick of making one nucleon spectator or the other and switching, basically they measured the proton-proton antineutron and proton-antiproton, proton-proton-antiproton. And the result is that the cross-section as a function of xf, the Feynman variable, is something like this for the antiproton production and something like 20% larger for the anti-neutron production. Okay? But still, this is not yet confirmed. There is a proceeding and we need more measurements. And in a few years, we will have also data for the production of anti-neutron. So do you think this difference of 20–30% is a big deal for astrophysical production of antiprotons? Is that important, or okay, is, let's say, an effect that we have to take into account, but is not that important for dark matter search? No, but overall, consider that we can do two. Basically, the typical assumption that is done is that we take proton-proton antineutron exactly the same as proton-proton antiproton. Instead, from a proceeding, it seems that this is a factor of 20–30% larger. Okay, so this variation of 20–30% is that important for the predictions of secondary production? The answer is yes, a lot, because as I said here, the prompt production has an uncertainty of 10%. So this 20–30% of uncertainty for the antineutron yield is at the moment the largest uncertainty for the secondary production. It's a dominant one. So there is a lot of effort in the collider and the accelerator community to measure this antineutron. And this effort is one perfect example of the multidisciplinary study between different fields of physics, because some colleagues, for example, Fiorenza Donato, put a lot of effort in talking with LHC experiments in order to measure this process, okay? And after years and of work, in the next years, we will have probably the first publications about this process, okay? And just to show you how this is really important for dark matter search, I show again some plots for the secondary production with respect to data. So these are a few papers where more or less you see that the secondary production seems to be roughly compatible with the data, right? So overall, there seems not to be a need of dark matter. But actually here, the data points are slightly higher with respect to the blue curve. And here is probably even more evident. And here you see other two papers. In particular, this one, you can see the ratio between the data and the best fit of the secondary production. And there is, in fact, a very small bump at 10 GeV, 10 gigavolt. The problem is that this excess, that is of the order of 10%, if you just take, let's say, the secondary production without any uncertainty, this is actually very, very significant, because it's beyond 1 sigma of the errors for 20 data points. So, generally speaking, this is a very significant excess. But the problem is that theoretically, for astroparticle physics, we have this, let's say, at least at the moment, they have been generous here, but I think the uncertainty is actually larger. So probably you have a 20% uncertainty here for the cross sections. So we have proposals to measure these cross sections with an uncertainty below 5%. So if we can basically narrow this uncertainty band of 5 to 5%, we can measure if this excess is significant or not. Okay. There is also another very important point about this excess, in my opinion, that this is a localized bump. So this is a bump localized, let's say, around 5 to 40 GeV, okay? Instead, the secondary production, even if you change your cross sections and propagation parameters, is more or less the same. So it's very, very difficult to change the propagation or the cross section in order to add a bump-like feature here. Okay? So typically when you have bump-like features, it's very, very easy to fit them with dark matter. It's more difficult to fit a bump by changing propagation parameters or cross-section parameterizations. Okay. Okay. In addition to cross-section uncertainties, there is another very important point to keep in mind that is related to the cross-section, to the AMS data uncertainties. In fact, what the experiment AMS released is the statistical and systematic uncertainty for each individual data point. But they have not released yet the errors for the correlation of the data points. So you can have uncertainties that not only affect 1 point, but affects the 2 points that are close by. Okay? So these are correlation uncertainties. In order to take into account the correlations between data points or systematic uncertainties related to the correlation, you have to use in your analysis the covariance matrix. So if you use the covariance matrix, your chi-square analysis basically takes into account the sum over all the bins and all the combination of bins ij, where you take into account the flux of your experiment for the bin I minus the flux of your theory for the bin I. Then you have the covariance matrix for the bin ij, and then the flux for the experiment at the bin j minus the flux of the theory for the bin j. Okay? So if you have 10 data points, you have a 10 by 10 matrix. The diagonal gives basically the errors if the data are not correlated. So we can write if Vij is equal to the delta Ij sigma squared. This is the typical case where you don't have correlations. And so the error square of the data is in the diagonal of the covariance matrix. At the moment, we only have the errors in the diagonal. So we don't have errors for the correlation. There have been papers where they have tried with very reasonable assumptions to estimate the correlations between the different data points. And they have found the covariance matrix that you see here. In particular, this one on the left is for antiproton. This one on the right is for the antiproton over proton. In case of the ratio, antiproton over proton, typically the errors and the correlations are smaller, because using the ratio, systematics on the numerator and denominator cancel out. Okay? So typically when you do ratios, you have less uncertainties. In fact, the yellow color, this is 1, so meaning basically no correlation, is broader in the case of use antiproton over proton. Instead, when you use antiproton, you see that the yellow is more concentrated really on the uncorrelated part of the covariance matrix. And in both cases, correlations seems to be important because you have even like 20% here in this region. Okay. So including the correlations, different papers basically find that the significance of this excess seems to be between 0 and 3 sigma significance. Okay, is not that significant. In the future, AMS will release more precise data. They have changed also the data analysis and they improve significantly the energy resolution, the charge resolution, the momentum resolution. And with more data and with this new analysis, we expect to have much more precise antiproton data. And hopefully they will release the covariance matrix. Okay, in this way we cannot, basically we don't guess, and we have really something that is fully reliable. But generally speaking, as Pedro also showed a few days ago, the antiproton excess can be fitted with dark matter with a mass and cross-section that is compatible with the galactic center excess. These are 3 different papers showing exactly basically similar things. So a dark matter mass of the order of 60 GeV, and the thermal cross-section is compatible with both excesses. And as you might remember, 310 to the minus 26 is the magic number for dark matter hunters because it gives the right relic abundance. Okay, so it's also compatible with the cosmological observations of dark matter. But of course, in order to really claim that we have discovered dark matter, we need a lot of works from different disciplines. So from particle physics, so accelerators, multi-messengers observations for pulsars. We really need a lot of work. Did I forget anything about antiprotons? No, I don't think so. Any question? How we measure theoretically the flux of antiprotons? So we take the propagation equation. We assume the source spectrum related to the process that you want. So source spectrum or secondary of dark matter. And then you solve the propagation equation. In order to solve the propagation equation, you can use semi-analytical methods that work if you neglect inhomogeneities of diffusion, magnetic field. So if you take your framework homogeneous in the Milky Way halo, you can find easy a semi-analytical solution. Instead, if you want to do something more refined, where, for example, you take into account that the gas is only on the thin disk, the interstellation field has a shape with the z direction, etc., you need to solve the propagation equation numerically. And there are tools like Dragon, Galprop, CRProp, etc., that solves numerically the propagation equation. Yeah, sorry. Exactly. Exactly. Yes. Yeah. Other questions? Otherwise, we move to the last part of antinuclei. Okay. So I left at the end what, in my opinion, is I think the most promising way of finding dark matter in indirect detection. That is using antinuclei. And actually here in this room we have one of the author of this idea, Nicolao, that together with Fiorenza Donato and Pier Salati, they have been the first to theorize the fact that antinuclei can be probably one of the easiest smoking gun signature for dark matter in indirect detection. The idea is actually extremely simple, and it's the following. So if you take the secondary production of antideuteron, for example, here you have to satisfy the baryonic number, okay? So the incoming proton must have an energy that is much larger than the deuteron energy, the deuteron mass to generate the antideuteron. And the reason is that you have to do at least antideuteron, proton, proton. So we have baryonic number equal to 0. But here you have baryonic number of plus 2. So you need at least other 2 protons. Okay? And in order to calculate the minimal energy of the incoming proton, we can assume that we generated all these protons at rest, and also antideuteron is at rest. Okay? So the idea is that you have an incoming cosmic ray colliding with an hydrogen atom of the interstellar medium, and this makes basically 6 nucleons, okay, with the mass of the 6 times the proton mass. If you do the calculation, so here you have basically the typical laboratory interaction. So this is 2 times mass of the proton, energy of the proton plus mass of the proton. This is the square root best of the initial process. And in the end, you have 6 times the mass of the proton. Now we want to find EP, so we square everything. We divide by 2, so you have 36 divided by 2, so 18. Minus 1, you get that the incoming proton must have an energy of at least 17 times the mass of the proton. Okay? So this means that the secondary production of antideuterons can occur only if the incoming cosmic ray proton has this energy. Okay. Let's talk now about the dark matter production. In dark matter, is there a similar limit for the deuteron, antideuteron, basically we have to keep in mind that if the incoming proton must have at least this energy, this means that it's very unlikely to create antideuterons closer to the rest mass energy of antideuteron, okay? Because the antiproton, the proton here is energetic, okay? Do we have the same low energy limit, low energy cutoff for dark matter? Do we have any issue with the baryonic number conservation of the initial and final state? At the beginning, dark matter, here there is no baryonic number, okay? So we don't have to basically make a proton such energetic to create an antideuteron. For dark matter, we don't have the issue of the conservation of baryonic number at the initial states. This makes the production of antideuteron from dark matter much larger with respect to the one of secondary production at low energy. So basically, if you take here 1 GeV over nucleon for the kinetic energy of the antideuteron, this is 0.1. For a typical thermal relic cross-section and a dark matter mass between, let's say, 50 GeV dark matter mass, this is the expected shape for the dark matter production, and this is for the secondary production. And the difference in normalization is huge. So this is the expected flux from dark matter. This is the expected flux from secondary production. And here between 10 to the minus 1 and 1 GeV over nucleon, you see that there are 2-3 orders of magnitude. Okay? Then here you see the expected sensitivity of some experiment, like GAPS, that is a balloon flight that will fly probably this year, AMS. So if these experiments will measure even one event in this energy window, this could be a dark matter discovery, because the secondary production is too far to explain these events. Okay, so the antideuteron signal is a signal that is very, very clean on the point of view of possible astrophysical backgrounds. Okay, now to be honest, here we are really considering a specific energy window, a specific dark matter mass. So instead, if the dark matter mass is probably above 1 TeV, all this peak of dark matter moves at higher energy, and so the secondary production, the dark matter production, starts to overlap, and so the disentangling the two contribution becomes more complicated. Okay, but generally speaking, antideuteron are probably the cleanest way to detect dark matter signal. Yeah. Yeah, exactly. Yeah, you're right. Exactly. Yeah, if you overshoot the peak of the secondary, you can increase also the dark matter with respect to the secondary. There is probably a mass in between where the two are instead very degenerate. Exactly, the unlucky point, yes. So how we calculate theoretically the spectrum of anti-deuterons and anti-helium. So we do this by using the coalescence. So the idea of the coalescence process is that in case of dark matter, or also the secondary production proton-proton, you generate, for example, quarks or gluons, and these particles hadronize. They hadronize within a few femtometers. Within a few femtometers, you could make an anti-proton and an anti-neutron that can move enough close in space and with the difference in momentum very small, that they make a coalescence and they make an antideuteron. So the first papers with coalescence, they were just considering a difference in momentum in the reference frame of the antideuteron that was supposed to be smaller than a p0, that is the coalescence momentum. Okay, so if you check that you have one antiproton, one antineutron with a value of difference in momentum smaller than p0, where p0 is typically 0.2 GeV, okay, then you have formed an antideuteron. This criterion is not very safe because you can have even this case where you make an antineutron, another antineutron. This antineutron decays, and these two antineutrons, actually they overlap in momentum for this condition. But then this antineutron decays first into an antiproton, and so this the momentum of an antiproton is similar to the one of the antineutron, as I said, and you think you have produced an antideutron. But actually this is basically impossible, because the antineutron decays after, I don't know, meters, kilometers, okay, depending on. And so the probability that these two particles are also close in space, it's very, very small, okay? This is an extreme case, but you have also other particles that are weakly interacting and they make antiproton, antineutrons. For example, you can have the anti-lambda B and other particles, okay? So when you have a particle that has weak decays, you have to take into account also a space criterion. So the antiproton, antineutron must be close in space with a distance that should be of the order of the size of the deuteron that is similar to the hadronization time scale. So typically we also include the difference in space that should be smaller than a few femtometers. Okay? Okay, then how we implement this coalescence criterion in our calculations? We can, it's difficult to do this analytically because you have to make these processes. It's not that easy to get antiproton, antineutron close in space and momentum. So typically you do run with Monte Carlo generators like Pythia. You do a lot of collisions of proton-proton or dark matter-like interactions. You check that for every event generated, you have an antiproton and antineutron, and you check whether they have these conditions satisfied. And then if the condition is satisfied, you save the kinetic energy of your anti-deuteron, you save these kinetic energies into a vector, and then you bin your kinetic energy and you count the number of anti-deuteron you have in a different kinetic energy bins, and you get the spectrum. Okay? Okay, perfect. Then you have to, in some sense, you have to calibrate your coalescence momentum, because the coalescence momentum and also this minimum size, this minimum distance in size should be calibrated in some way. And we have two sets of data. We have Aleph data at LEP that is referred to the anti-deuteron production after hadronic decays of the Z resonance. Okay, so you make it plus and minus at 92 GeV, and you select only hadronic decays, and you check whether you have made anti-deuteron. There is one single data point for this measurement that gives the multiplicity of anti-deuteron in this process. And this is typically the measurement that is used to tune dark matter production of anti-deuteron, because we expect that these processes are electroweak processes similar to E plus E minus. Instead, in order to calibrate the secondary production, we typically use Alice data above 900 GeV in the center of mass energy. These data are actually much more precise because you don't have only one data point, but actually you have a distribution of number of events as a function of PT. For energies at 900, 2 GeV, 7 GeV, 14, 2 TeV, 7 TeV, and 14 TeV. But this is what is expected for secondary production. Okay. At the moment, it's not clear whether the coalescence momentum and the difference between the position of the antinucleons is something that changes with the energy scale. It changes whether you use proton-proton or E plus E minus. In fact, several papers find different values for this P0 when they fit Aleph data or when they fit Alice. And the value can change from basically 0.16 to 0.24. Okay. The problem is that the source, basically the flux of anti-deuteron scales roughly with the coalescence momentum to the third power. So a difference between 0.16 and 24 makes the flux uncertain by a factor of 200-300% or even more. Okay. Recently, with Nicolaou and other colleagues, we did a new analysis where we calibrate different models of coalescence. We found that the difference in space of the antinucleons should be of the order of a few femtometers. The coalescence momentum should be, for this specific model, roughly 0.2 GeV. And actually, the prediction for the spectrum of anti-deuteron using these different models is quite similar. So you have uncertainties of the order of 10-20%. Okay. So when you calibrate properly your propagation, your coalescence model, actually the final spectrum, even if you use different coalescence models, actually is quite similar. Okay. But this has been done using Aleph data. So we still have to check whether using ALICE data for anti-neutron production, we get more or less the same results for the correlation parameters, or we have different results. So basically, we still have to check whether the correlations is energy dependent and process dependent. Okay. Then let me summarize with this table what we have currently for interior detection. So for gamma rays, we have seen that the galactic center excess is a very good target. Theoretically, we expect that this is the brightest direction for gamma rays. The interstellar emission model gives a very large uncertainty, but we already detected an excess. And so in my opinion, the potential discovery is very, very large for the galactic center. For dwarf galaxies, we have a lot of dwarfs. In the future, JWST, LSST will increase significantly the sample of dwarfs. Dwarfs are very, very clean astrophysically. We don't expect big astrophysical contribution. So in this case, we are basically signal dominated. We are not background dominated. So the studies of astrophysics is not that important. And so I gave this a high potential because it's, if we detect something, very likely is dark matter. Positrons, instead I put a medium because it's tricky to get the pulsar contribution. So for secondary, we have quite a precise estimate, but we still don't know how much pulsar contribute. So we need multi-messenger study from radio to gamma rays in order to estimate the secondary production. Antiprotons, we have an excess. It's pretty small now. It's probably not very significant. We need to reduce significantly the cross-section uncertainties, and there is a big effort in the accelerator community to reduce these uncertainties in the next 4 or 5 years. And also AMS will probably improve the errors on the data. For anti-deuteron, I gave a very high, as for the galactic center, because it's probably the messenger that could be the cleanest on the point of view of astrophysics versus dark matter. And also we have 2 experiments at least that will probably give results in the next few years. One is GAPS, that is a balloon flight by NASA, that will fly probably, or hopefully, this year. AMS instead has already the data. So they already collected data since 12, 14 years probably. And they already detected actually some events of anti-deuteron, what they said, but they have not a precise study of the systematics. So they still don't know if these events of anti-deuterons, they are really anti-deuterons, or they are maybe deuterons with the not right angle and curvature measurements with the magnet. Okay. Okay, so I stop here and I take questions. Yeah. You take this into account because when you model the source distribution, gas distribution, you don't stop your map at the line of the galactic center. You also include the gas and source distribution behind the galactic center. Then the question could be, are you sure that what you're modeling behind is precise as what you measure in front? The answer, of course, is we are not as sure as what we have locally. And this is part of the interstellar emission uncertainties that we have to reduce. Okay, but also consider that the farther you go, and the less that component is important. Okay. Yeah. Mm-hmm. Yeah. Yeah, absolutely. So theoretical physicists have a lot of imagination, so we created a lot of models that are very diverse. So there are models that annihilate preferentially to quarks. For example, singlet scalar model for masses below 100, it goes basically all to BB bar. Instead, we have other models like the L mu minus L tau model, that instead annihilates preferentially into mu tau and the neutrino mu, neutrino tau. If you have a model like this, you have no hope to detect antideuterons. Also, the production of antiprotons should be negligible, but you can fit the Galactic center excess. Okay, so in fact, in my career, I started to transition from a model-independent approach to instead studying specific models that, of course, must be simple, because I think that simplicity is a criterion that we should use first. And using a specific model is very helpful because you have predictions for the relic density, for collider, direct detection. And this is something that you cannot have if you have a model-independent approach, okay? So since we are starting to claim that there are some signals, some possible signals, I think it's important to start using specific models, because if there is a signal in the galactic center, but we don't see anything in antiproton, antideuteron, we have strong bounds from direct detection, we have to match the relic density. Is still possible to fit the galactic center excess with dark matter, considering all the rest? Maybe the answer is no, and so we rule out a dark matter interpretation of the galactic center excess. If you just study a model-independent approach, you don't have an answer for this. Yeah, of course, it's not easy to the model-dependent approach because you have tons of models. But yeah. Yeah, or maybe you have excesses in antiproton dwarf and galactic center excess. Is it possible to match all these anomalies in one unique framework? If you use a specific model, you can answer. Other questions? Okay, so if not, I just remind you the workshop we are organizing in Torino. So the name is Dark Tools, and I hope the best for your future. Okay, thank you.